Let's look at some Laplace transforms, especially with respect to elementary functions. Okay, let's look at the first one. Laplace transform of e to the power of kt. Remember, Laplace transform 0 to infinity of e to the power of kt. Here this is f of t times e to the power of minus st dt, and this can be written as 0 to infinity of e to the power of t is common. We want minus outside, so minus, so s becomes plus, k becomes minus, t is common dt, and this would be e to the power of minus s minus k t, and a minus here, and s minus k, 0 to infinity. And here let's apply, if we apply infinity, what happens? Remember, as t goes to infinity, this is e to the power of minus, so which means it goes to the denominator. So denominator goes to infinity, which means what? The number becomes 0, right? Plus, and here when it is 0, it becomes e to the power of 0. E to the power of 0 is 1. And remember, here actually it will not be plus, it will be minus 1 by s minus k. This minus is because of this, no, because of this, and this minus is because we are subtracting by substituting 0. So this becomes 1 by s minus k. Now, if s minus k is less than or equal to 0, let's say less than 0, what will happen, right? S minus k is less than 0. This is negative. That means this will become plus, right? So which means power of e is plus, is positive, which means what? Which means the integral, or basically not integral as such, the function diverges. So since the function diverges, that means it goes to infinity, we can't really do anything. So the integral also diverges. If s minus k is equal to 0, then what happens? If s minus k is equal to 0, then 1 minus s minus k will become 1 by 0. That means it will become indeterminate. Remember, it may be k, or it may be a, or it could be any letter. Okay, so that is why this s minus k has to be greater than 0. That is the requirement. If k is equal to 0, then what happens? L of 1 be equal to 1 by s minus k. K is 0, so 1 by s. Again, for s greater than 0. Remember, we looked at Laplace transform of e to the power of kt. What happens if it is minus kt? Then in that case, what will it be? Just keep, follow the same procedure. Minus kt, this is now the f of t, times e to the power of minus st dt, right? So this becomes 0 to infinity of e to the power of minus, we take it out. So it becomes s plus k t dt. Same pattern emerges. If you see here, since the same pattern emerges, instead of s minus k, we have s plus k. So this would be what? This would be 1 by s plus k. Again, remember, s plus k has to be greater than 0. So this is one you have to remember. This is Laplace of e to the power of minus kt. Laplace of e to the power of kt is equal to 1 by s minus k s minus k greater than 0. And remember, Laplace of 1 is equal to 1 by s, where s is greater than 0. These are things that you have to remember. Okay, now let's look at the next category. Laplace of cos of mt. It can be mt, it can be at, whatever. And naturally, along with that, we will also be looking at Laplace of sine mt. Now, whenever this type of situation arises, what we'll do is we will consider this I theta is equal to what? Cos theta plus I sine theta. This is the identity that we'll invoke. Now, what we'll do is we will say theta is mt. So what happens to this? It becomes I mt is equal to cos mt plus I sin mt, right? So we are getting cos mt as the real part of this function. We are getting sin mt as the imaginary part of this. Now let's proceed. Now instead of focusing on cos or sine, we will focus on this. So e to the power of imt is equal to Laplace of cos mt plus I Laplace of sin mt. Remember this linearity, and we also know how to write it in the Laplace transform form, integral form. So 0 to infinity of e to the power of minus st times e to the power of imt dt. So now we are writing this in integral form. Let's just keep solving it. What happens? We can write this as 0 to infinity of e to the power of, remember minus, it the quantity has to be negative, so minus will be outside, s minus im, and t is common, dt. So which means, what is it going to be? This is going to be 1 by s minus im. Remember s minus k. If it is s minus k, here also it will be s minus k, and here k is im. We want to get rid of this I from the denominator. So let's rationalize it. S plus im by s plus im. What do we get? S plus im by s square minus im square, which is equal to s plus im by s square. This becomes I square. I square is nothing but minus 1. So plus m square, and this can be finally written as s by s square plus m square plus m by s square plus m square I. We can write either I on this side or on this side, right? So this is, remember, this is for the Laplace transform of e to the power of imt. So for the cos, what is it? It is going to be the real part, and real part is s by s square plus m square. Similarly, Laplace transform of sin mt is equal to the imaginary part. Now the imaginary part is m by s square plus m square. Okay. Similar to sine and cos, let's look at hyperbolic sine and cos. So Laplace transform of cos mt and Laplace transform of sin h mt. Now remember, cos mt. Cos mt can be written as e to the power of mt plus e to the power of minus mt by 2. Laplace transform of cos mt is equal to Laplace transform of, remember 2 is constant, so we can actually take it out. So we can actually write it as 1 by 2 Laplace transform of e to the power of mt plus e to the power of minus mt. And remember, we can split it. So 1 by 2 Laplace transform of e to the power of mt plus half of Laplace transform of e to the power of minus mt. This can be written as what? Remember, half remains as it is. L e to the power of kt we have already seen, remember? So this is nothing but 1 by s minus m plus half. I have taken it out. Again, e to the power of minus kt. Remember? So that is nothing but 1 by s plus, now it is simple algebra, s square minus m square, s plus m plus s minus m. M and m gets cancelled. Half of 2s by s square minus m square. 2 and 2 cancels. So s by s square minus m square, which means Laplace transform of cos mt is equal to s by s square minus m square. And similarly, Laplace transform of sine, hyperbolic sine of mt is going to be m by s square minus m square. Okay. Fourth one. Let's say the function f of t is equal to t to the power of n, where n belongs to the natural numbers. So Laplace transform of t to the power of n would be equal to integral of 0 to infinity of t to the power of n times e to the power of minus st dt. This is equal to, and remember now we have to do integration by parts. This would be minus t to the power of n times e to the power of minus st by s plus integral of 0 to infinity. Remember uv minus integral of udf, I think, or vdu. Okay, so now this would be e to the power of minus st differential of tn. So ntn minus 1 by s dt. Now remember, this is 0 to infinity. So let's evaluate this between 0 and infinity. So this becomes, see, when we take infinity, e to the power of minus infinity it becomes, which means it goes to the denominator. So the denominator goes to infinity. So which means this whole thing becomes 0. Now similarly, when we substitute 0, what happens? So this becomes a 0, this t becomes 0, which means the numerator becomes 0, which means overall this is 0 plus integral of 0 to infinity of e to the power of minus st t to the power of n minus 1 dt. And what we can do is we can take this n and s out. Okay, now what is this integral? This integral is nothing but the Laplace transform of t to the power of n minus 1, right? So basically what we have done is t to the power of n, Laplace transform of this is n by s times the Laplace transform of t n minus 1. If we follow the same steps, because now this we have to evaluate now. We can't just leave it as it is, because if we were going if we were going to get stuck here, we would get stuck here as well. Let's look at this. Laplace transform of t to the power of n minus 1 would be equal to what? N minus s remains as it is. Then what comes? Because here, if you notice, here what do we have? N, we have t to the power of n. So this is n by s. Here instead of n we have n minus 1. So this would be n minus 1 by s. And times Laplace transform of, by the way, this n minus s we don't require because we are evaluating only this part. Laplace transform of t minus 2. Now Laplace transform of t n minus 2 would be what? N minus 2. This would be n minus 2 divided by s. Laplace transform of t n minus 3. Now do you notice n is some value and we keep subtracting it by 1. So as we keep subtracting, so finally we will reach Laplace transform of t to the power of 1, which is equal to 1 by s, and finally Laplace of t to the power of 0. See, whatever is in the exponent will come in the numerator here. So it was n minus 2, n minus 2, 1, 1. But now what about this? Now L t to the power of 0 is equal to what? That is nothing but Laplace transform of 1, which we have already seen is 1 by s. So which means Laplace transform of t to the power of n is this times this, which means this times this times this times. So we have to multiply all the right hand sides. So Laplace transform of t to the power of n is equal to n by s times n minus 1 by s times n minus 2 by s, and so on. It will go till 1 by s, and finally times this one, 1 by s. Now look at the numerator. What is it? N times n minus 1 times n minus 2 and so on, 5, 4, 3, 2, 1. That is nothing but n factorial divided by. Now s is being repeated how many times? See, up to 1 it is n times. But here we have one additional s. So we have s to the power of n plus 1. And remember always that s is greater than, what about L of t would be equal to 1 by s. Remember, this is t to the power of 1. So 1 by s will come as it is times t0. That means 1 by s, which is equal to 1 by s square. Okay. What about t2? This would be what? 2 by s times 1 by s times 1 by s, which is equal to 2 by s cube. T cube would be, now this would be 3 by s times 2 by s times 1 by s times 1 by s, which is 6 by s to the power of, okay, and that's how it will go. Okay, now let's look at other elementary functions. E of a t times t to the power of n, Laplace transform. What will it be? This would be n factorial by s minus a to the power of n plus 1. Remember, t to the power of n gives you n factorial by s to the power of n plus 1. E to the power of at gives you that s minus a. Okay, let's look at the next one. Laplace transform of EAT times cos mt. If you just look at cos mt, it is s by s square plus n square. But here now, because of this at, this would become minus a square. Similarly, Laplace transform of EAT sin mt. This would be what? If you just look at the Laplace transform of sine mt, it is m by uh, s square plus m square. Now, because of this at, e to the power of at, this would become s minus a square plus m square. Okay, what is left out? Hyperbolic. So e to the power of at cos mt, just cos mt is what? Is s by s square minus m square. Instead of m plus m square, it is minus m square. So this would become what? S minus a by s minus a square minus m square. This minus is the only difference from the sixth one. Similarly, Laplace transform of EAT sine hyperbolic MT is equal to, and here m by s minus a square it will be instead of just s square. So s minus a square minus m square. Basically, the advantage of looking at and remembering these elementary Laplace transforms of elementary functions is that for other more complicated functions, you can somehow manipulate those functions to come out with these elementary functions where you can directly do substitution. Okay, I think that's enough for now. Bye.